So I want to clarify a couple of things, and then I'm going to show you the world's worst video. I'm so proud of this. I can show you the worst video I've ever seen. But anyways, so for chapter 13, you need to know this. Can you dose milligrams per kilogram? Have we practiced calculating a dose based off of weight, milligrams per kilogram? We're going to do that again today. We've also practiced determining concentration or using concentration to take a dose in milligrams to say a volume of an additive. We know concentration is the amount of something in something else, okay? Milligrams per milliliter. What's new today to some extent is infusion rate. All right, so I need you to understand that. When I say the word rate, what unit needs to come to mind? Time. A rate has something to do with time. So an infusion rate is an amount per time. And if we're infusing it, if we're administering an IV product into a person, we are usually putting some volume per time. The concern here is, or the difference here, different units of volume. So what is one common unit of volume? Milliliters. So a very common administration rate is milliliters per minute, or milliliters per hour. Would you agree minutes or hours are both units of what? Time. So in these questions, you have to be careful. What are the units I'm using in my infusion rate or that I'm solving for? Look for the unit of the volume, look for the unit of the time. My video here is about this. What's new is one of the units that have traditionally been used for administering IVs to products in time is drops per minute or drops per hour. The unit of a drop. It is the worst unit ever because what is the metric amount of a drop? There is no standard metric amount for a drop because different sets will have different drop sizes. So I'm going to show you a video here of a nurse who's going to try to talk a little bit about how do they. If you tell somebody and you tell the nurse to infuse something at 15 drops per minute, what does that mean? What is the drip chamber? So as you're looking at this IV, look to where she's seeing, and I'll show you in the second part of the video, you'll see some drip chambers. That's where you look and count the number of drops that drip per amount of time and how you regulate it, all right? Then the last part of this video, which is kind of weird, I'm trying to show you different size drops, okay? There's bigger drops, and then the last video is going to show you a set with a little needle sticking into the drip chamber that makes very little drops, such that you can get 60 drops per mil versus something like 15 drops per mil. So remember, it's the set that determines how many drops you get per volume, all right? So let's watch this video. This may be something you've not experienced before in terms of administering a drug. When we label the infusion rate for nurses, sometimes we tell them to administer things in drops per minute or drops per mil, and this is what that means.
Clamp and your watch, so it's all sort of handy and visible, and you're going to start that counting. So we wanted about 21 drops per minute, so you're really just going to start estimating what that is and timing it maybe in increments of 15 seconds and then waiting for a full minute to make sure you get that 21 drops in a minute. So you can see it dropping and you're just going to be counting those drops. 1, 2, 3, 4. That's probably a little fast. So then you're just going to want to tighten up your roller clamp a little bit. So you will want to make sure you're at that accurate drop rate before you hook up to the patient because you don't want to be doing that regulation when it's hooked up to the patient already because you may be inadvertently giving them too much fluid or not enough. So you want to kind of do it. It will make things a little bit wet, but that's again sort of one of the minor downsides of using gravity. The other one is obviously that at any time somebody could come and fiddle with the roller clamp or maybe the person lies on it. So we do prefer the pumps.
Now, these are large drops. Look at the kind of the size of the drop. You'll see larger ones here compared to the next one, which shows you some smaller drops going into the drip chamber at a certain rate of drops per time. Is microtubing. You can see how much faster the drops form because they fall off there sooner, meaning the volume for each drop is less. It's a smaller drop, so there'll be more drops per milliliter. The number of drops formed per volume is smaller for these smaller sets, okay? So, thank you for surviving that. So, point being here, when you read my questions here in a little bit, I'm going to need to provide you some information about the administration set. an administration set has a calibration to it. How many drops per milliliter? As I just tried to show you, different sets will have different size drops formed, so the number of drops per a standardized milliliter will be different. So part of what you'll need to do if you're going to be calculating an administration rate in drops per time, you're going to have to convert a volume in milliliters to a number of drops. So you always have to look at the information provided about the set being used, all right? In this case, we're talking about infusing IV fluids, all right? So in this question one, it says a patient is to receive 500 milliliters, it's a volume, of lactated Ringer's solution, okay? So the question is, first part, is using the administration step calibrated to deliver 15 drops per milliliter? That's a calibration, 15 drops per mil. How many total drops are contained in a 500 ml bag? That's just helping you understand this is calibration is a conversion that allows you to convert from volume, usually in milliliters, to drops. Remember, it's not a constant. It has to be provided to you because it can be different in different questions. Here we have 15 drops per mil, so that's pretty straightforward. If we have a 500 ml bag and we have 15 drops per milliliter, multiply by 15 because 15 drops per mil, then mils cancel, and we get 7,500 drops. So really, this bag is both 500 milliliters and 7,500 drops. It's just a different unit of volume, if you will, all right? So let's back up a little bit and say, okay, now, if the IV administration pump is set to administer these 20 drops per minute, how many hours will the infusion last, all right? It's convenient that we can actually now start with drops because we know my bag contains 7,500 milliliter drops. So for my previous answer, I'll start with that and say, okay, if that's the volume of my bag in drops and I'm going to administer 20 drops per minute, then if I divide by the 20, drops cancel and I convert my number of drops to my number of minutes. All right, but it wants to know time in hours, so I need to convert minutes to hours by dividing by 60. Minutes cancel, and I can find that that 500 milliliters is equivalent to 7,500 drops, which at an administration rate of 20 drops per minute will last 6.3 hours. So at this point going forward, I just want you to realize this is an important answer here. That bag, this 500 milliliters, contains this many drops and is going to be administered over 6.3 hours, because that's kind of the start to the next question. The next question says, well, okay, the solution contains 130 milliequivalents per liter, that's a concentration. What is the infusion rate expressed in milliequivalents per hour? We said an infusion rate is a certain amount per time. And in this case, my time is hours. But instead of volume, I want to express it in milliequivalents. So this was the hardest part of this question is where do I start? We want an infusion rate in these units. I would argue we don't know that. But I would argue we do know an infusion rate in other units because I'm going to be infusing how much? 500 milliliters. What was the answer to my previous question? 500 milliliters has to last how long? 6.3 hours. So that's where I'm starting from. I'm going to start from the fact that I have 500 milliliters infused over 6.3 hours. What I need to do is convert it to these units, and hours are already there, so I don't even have to convert time. The question and the hard part is how do I convert milliliters that I'm starting with to milliequivalents? Well, I have my conversion here, but my conversion is based off of liters. So the first thing I have to do is divide by 1,000 so that I convert milliliters to liters, okay? So I now in liters per hour. Then I can use that conversion of 130 milliequivalents per liter that my bag contains. If I multiply by that, liters cancel. That gives me units of milliequivalents over hours. So if I go ahead and do that math and do all my multiplication and dividing, if I divide it all out, I get 10.3, and my units are in milliequivalents per hour. The trick was being able to set up an initial infusion rate. Given the information you had and that you calculated, you had a bag of 500 mils that was going to go in 6.3 hours, and we ultimately converted it to a different infusion rate with different units, but it's just unit conversion at that point. Okay, so can you visualize an infusion rate? It's a volume per time. Volume can have different units, time can have different units. All right, let's move on to some dosing questions. That was kind of a just straightforward infusion. Now let's do some dosing for Remicade. And I'll try to just be quick. We have a patient who weighs 132 pounds. We know the dosing is 5 milligrams per kilogram, so this is hopefully something you can do very quickly and very carefully and consistently. Oh, Larry, go back. So anyway, so 132 pounds. I've got to use my conversion of 2.2 pounds per kilogram. So if I divide by 2.2, I convert that 132 pounds to 60 kilograms. All right. Now that I know their weight in kilograms, I can use the dosing at 5 milligrams per kilogram to multiply that across and see that I need a total dose of 300 milligrams. Okay, chapter 7 and 8 stuff. Hopefully you're good with that. And that's kind of where we stopped. But now with IVs, we need to turn this into a product that we can then actually infuse and administer. So where do we have to go from the total dose? The next question says, well, the Remicade, the drug, is available in a IV vial that contains 10 milligrams per mil. All right, so what volume, now that you know the dose, tell me the volume of this additive that I need to add to my IV bag to provide my dose. Well, my dose was 300 milligrams. If the concentration of my vial provides for every 1 milliliter has 10 milligrams, then if you divide by 10 to cancel milligrams, 300 divided by 10 is 30, meaning I need 30 milliliters of a 10 milligram per mil to provide me my 300 milligrams. So this is my drug additive volume. Could I just inject that and give them the right dose? Yes, if you inject 30 mils of this liquid, it would provide them 300 milligrams. But some drugs have too low a pH. Some drugs are caustic and they have to be diluted. So we don't want to inject the pure drug solution. We need to dilute it further so that the concentration we administer is safe for the person. So in this question, I gave you that safe concentration, saying that the final drug solution that we administer cannot be 10 milligrams per mil. It can only be 2 milligrams per mil. So we're going to have to dilute that injectable solution so that it is no more concentrated than 2 milligrams per mil. This one is the tricky one. So I have a concentration in milligrams per mil, milligrams per milliliter. I don't know the volume, but do I know the dose? What dose do I want? I want 300 milligrams. That's how much I'm trying to administer. Well, if I can't have more than 2 milligrams per mil, so if I multiply or essentially divide by 2 milligrams cancel, that means I'd have to have 150 milliliters. Does that make sense? If I have 300 milligrams, what is 300 milligrams divided by 150? 300 divided by 150 is 2 milligrams per mil. So I basically found the volume, 150 mils, that when I divide into my dose gives me my desired concentration. In this case, no more than 2 milligrams per mil. So that's the total, but I want to emphasize total. I need my 300 milligrams in a total volume of 150 milliliters. So the question says, how much sodium chloride am I using? The normal saline is my diluent. So the total will be the combination of my drug plus my diluent. So if I take my total and subtract my drug, what's left is the diluent. So 150 total minus the 30 milliliters we calculated of the drug means I would need to add 120 milliliters of my diluent. In this case, isotonic sodium chloride solution, 0.9% sodium chloride, added 120 mils of that plus my 30 mils of drug gives me my 150 mils total, which would give me a 2 milligram per mil solution. Okay? I don't know if I described that well, but hopefully you can do those. Last question is just now, all right, of that solution, if we want to administer it over 2 hours, what do we tell the nurse to administer it in units of milliliters per minute? So this is an infusion time. Well, I know my volume's 150 mils. We just said that. We know that it's going to be over 2 hours, so I'm in milliliters per hour. All I have to do is convert hours to minutes by dividing by 60. So I end up with milliliters over minutes, and that gave me 1.3 milliliters per minute. All right. All right, let's do number 3, another dosing one here. It's pretty straightforward, I think. If a patient weighs 66 pounds for this drug, vasopressin, we need to know their weight in kilograms to do their dosing. So 66 divided by 2.2 pounds gives me 30 kilograms. Now I have a weight in kilograms. I can look at this dose. And I chose this drug because it has very small numbers. And instead of weight in milligrams, the amount is in units. It is units of units. So it's a little different, but the math is the same. So if I need to know the dose in terms of units per minute, I'll multiply by the weight, 30 kilograms times 0.002 units per kilogram per minute. Kilograms cancel. and I get 0.06 units per minute. All right, so that's my dose. But it's actually not just a dose, it's a what? It's a rate, because it's a dose per what? Time. I'm giving you units of units per minute. So it's actually an administration rate, okay? Now, going on to determine the volume here, it says if it's available in 1 ml vials containing 20 units, and I want this concentration, how many vials do I need to provide 250 mils? There's a lot of stuff there. Where do we start? What will determine how much drug? How much are we preparing? We are preparing 250 mils. This is the volume I want to prepare. So it's that volume that has to have that concentration. All right, and if I have that volume times that concentration, milliliters will cancel, it would tell me how much drug I need. Okay, 250 times 0.2, and I end up in units. Now, how many vials will provide those number of units? Well, if I know that's 1 mil per 20 units, then I just divide by 20, and I end up with vials. In this case, it was 2.5. Have to round up to a whole number of vials, so I would need 3. I wouldn't use all 3 vials. I'll use 2.5 out of the 3 vials worth of drug to provide my dose of vasopressin for a 250 ml bag at that concentration. Okay. So I would still argue the math is not hard. It is the setup, and I still suggest that you use the dimensional analysis or use your units to guide your math here a little bit and make sure that you're doing the right thing, whether it's multiplying or dividing. Okay? So now we get to the infusion rate. So if the infusion set is calibrated at 20 drops per milliliter, that's a calibration, what infusion rate in drops per minute? I want drops per minute. Didn't we already calculate a rate? I know that I want 0.06 units per minute, but I need to convert that number, 0.06 units per minute, into, what do I want here? I want it in drops per minute. So let's start with that, 0.06 units per minute. That we solved there in part 2. And let's just do unit conversions, all right? My minutes I don't even have to mess with. How can I convert my units of units to a volume, to a number of milliliters? Well, we were said in the previous one that this is the concentration. We calculated that. We were given that we wanted a concentration of 0.02 units per mil. So that's where that comes from. So if I divide by that, units of units cancel, and I'm now in milliliters per minute, all right? How do I convert from milliliters to drops? I use my calibration there, and if I multiply by 20, then milliliters cancel, and I end up with drops here and minutes here. If I do that math all the way across, I end up with 6 drops per minute, rounding to a whole number. Okay? So it's a little bit of a board game here. You need to kind of know what the terms are and then look at your units to kind of guide you there. All right? So, all right. I'm going to skip 4 for now for the sake of time. I'll hopefully come back to it, but I don't want to waste my time on 4 when 5 and 6 are good questions that I would hope that you could answer. All right? So skipping to question number 5. Okay? Onpattro is a siRNA treatment, so we're going to need to dose that. We were given a weight in pounds, 165 pounds, so the first step is to convert pounds to kilograms. 165 divided by 2.2 means this patient weighs 75 kilograms. Now I know their weight. I can use essentially that in patients less than 100 kilograms, it's 0.3 milligrams per kilogram. All right, so since we're at 75 milligrams, that works for us. 75 kilograms, I'm saying things wrong. His weight of 75 kilograms times 0.3 milligrams per kilogram will give me a total dose of 22.5 milligrams. Would you agree? I hope that this is easy. This is straightforward. Convert weight from pounds to kilograms. Take the dosing times kilograms to get a total weight now of 22.5 milligrams. From that dose now, we need to determine how much solution from a vial will provide that dose. My vials contain 10 milligrams per 5 ml concentration. So what volume do I need to prepare this dose? This is the dose I want. That is the concentration of my vial. So if I multiply so that milligrams cancel, I'll determine the volume in milliliters that I need to provide that dose. So 11.3 milliliters of this solution provides that dose. So that's what I need to prepare the dose. Like we said, though, you don't always just administer your vial solution because it's oftentimes too concentrated. All right? So what we need to do in this case, it says if the dose is mixed, and here I'm telling you, not a concentration, but I'm telling you to put it with 200 milliliters of normal saline. All right? Just remember this. Volumes are additive. So if I'm going to take 11.3 milliliters and add it to a 200 ml bag, will it still be a 200 ml bag? No, I'm not trying to make this rocket science, but remember when you add drug to an existing volume, the volumes are additive, so you need to know that this new bag, once my drug is added to the bag, is no longer 200 mils. It's the combination of the diluent volume plus the drug volume. So now I have 211.3 milliliters. This is going to be important because that's the volume I have to infuse to get the dose of my drug. So how much time does that have to be administered over? Okay. It needs to be administered over 80 minutes, and I'm going to be using a set that has 15 drops per mil. So now I want the infusion rate in drops per minute. And infusion rate is volume per time. So where do we start with? We have this volume, this 211.3 is the volume of both the drug and the diluent, that's combined. That's the volume that has to be administered over this 80 minutes. Volume per time is the administration rate. Then the last thing to do is convert it to the units you want. We don't want milliliters per minute. We want drops per minute. So I have to factor in the fact that there are 15 drops per milliliter. So if I multiply by 15, milliliters cancel. I do my math, and it ends up being a total of 40 drops per minute to infuse this volume of 211.3 over 80 minutes. And that volume provides me the total dose of the drug that I need at a safe concentration. Okay? I hope these things don't too hard, so let's do one more very similar question now. This is the most difficult in the sense that the dosing isn't always weight-based. Would you agree? What is another big dosing that we have practiced? Body surface area dosing. So in this drug, the clofarabine, we are not going to dose it off of weight. We are going to dose it off of body surface area. So as this should be a review, to calculate body surface area, I need to know two things. I need to know the weight in kilograms and the height in centimeters. So I'm starting here with 132 pounds, dividing by 2.2 to get it into kilograms. So I know the weight in kilograms. They're 5 feet 8 inches in height. So I'm going to start with 5 feet times 12 inches gives me 60 inches plus the 8. Don't forget the 8, so 60 plus 8 is 68 inches. Then use that conversion factor to convert inches to centimeters by multiplying by 2.54. So now not only do I know their weight in kilograms, but I know their height in centimeters. Does that all sound familiar? So why we're cumulative here, okay? So we got that. Then again, on a test, I'll provide you the Mosteller formula for body surface area. It's weight in kilograms times height in centimeters, divided by 3,600, and then don't forget the big square root. So let's do that. If I do that math, here's my weight times my height. Then here's the combined, divide by 3,600, I get 2.88. Take the square root of that, and I determine 1.7 meters squared. All that work just determined their body surface area. Now that I know that, I can calculate a dose, because I know the dose for this drug is 52 milligrams per meter squared. Since I know their body surface area is 1.7 meters squared, multiply that times the dose of 52 milligrams per meter squared. Voila, the dose they need is 88 milligrams. That's where we've kind of stopped in the past. Chapter 13 makes us go further. What are you going to do with that 88 milligrams? You need to tell me how many milliliters of an injectable solution of this drug do I need to provide 88 milliliters? Well, what do I know about the vial? It contains 20 milligrams per 20 milliliters, basically 1 milligram per mil. That's the concentration of the solution. So how many milliliters of this vial solution will provide the dose of the drug that I need? If I need 88 milligrams, times 20 mils over 20 milligrams, milligrams cancel, and I get 88 milliliters, okay? This is the volume of the what? Drug volume. Do we sometimes have to dilute that volume? Yes. So how do I need to dilute that drug volume? It needs to be diluted using 5% dextrose, okay? To a what? A concentration of 0.2 milligrams per mil. So if this is my target concentration, and I'm going to use dextrose, what volume of dextrose do I need? Well, it kind of depends on the amount of drug, right? So again, if I'm having 88 milligrams, and I don't want any more than 0.2 milligrams per mil. So if I multiply that so that, again, milligrams cancel, I determine 88 divided by 0.2 is 440 mils. I need to take 88 milligrams divided by 440 milliliters to get 0.2 milligrams per mil. That would give me the concentration I want. So this dose has to live in that volume to get that concentration. So that's my volume. My what volume? What did I say? Total volume. That is the total volume I would have to have that amount of drug in. So if that's my total, how much is coming from my drug that we just calculated? 88. So if I subtract 88 from my total, the amount of dextrose, the amount of diluent I need is 352 milliliters. That volume combined with this volume gives me that total volume. So this is the amount of dextrose that I need. So the last kind of question we typically ask is, again, a little bit about infusion. So now if the IV solution I'm using is going to have a set that, don't do that, has 15 drops per milliliter, what is the infusion rate in drops per minute if we're going to give my dose over 2 hours. I can't even read. 2 hours. So I know the time, 2 hours. What did we say the volume was going to be? We just solved for that. Would you remember? The total volume is 440 milliliters. That is the volume that has to be administered over 2 hours. There's my infusion rate. The problem is I need drops per minute in the end. So this is not drops and this is not minutes. So pick one. Which one do we want to convert first? I did time this time. So let's convert hours to minutes by dividing by 60. That converts the units of hours to minutes. Now let's convert milliliters to drops by using my 15 drops per mil calibration. By doing that, by multiplying by 15, milliliters cancel, and you can see now I'm going to end up with units of drops per minute, which is what I want. So you do that math all the way across, and you get 55 drops per minute. All right? Good. Now, I skipped number 4. I know I'm out of time, but here, let me just show you number 4 here on the key here. Number 4 is a lot of repetition here. The reason I had you skip this, when you get to the part 4, you have a total volume and you're going to have an infusion rate that increases. First every 10 minutes and then every 20 minutes, every 20 minutes, every 20 minutes, the infusion rate increases, so the amount infused over that time increases.